In this discussion video, we'll do an optimization example in which a rectangle is inscribed in a right triangle. This is problem 7 from worksheet 12, and it says, a rectangle is inscribed in a right triangle. The base of the triangle has length 16, and the height has length 12, and the hypotenuse is 20. The sides of the rectangle lie on the base and the height of the triangle. What are the dimensions of the rectangle that has a maximum area? Okay, so I want to begin by identifying what is it that I want to optimize. In this case, it says I want to find the maximum area. So I want to maximize the area. Okay, next thing I should do is draw a picture. And in this problem, it tells me there's this right triangle. So I will draw a right triangle. And it tells me that the base of the triangle is length 16. I'm going to just say that this side is the base, 16. The height has length 12. And the hypotenuse is 20. And then it says that we have this rectangle that's inscribed in the right triangle. And it says that the sides of the rectangle lie on the base and the height of the triangle. So that means actually that there's just two sides of the rectangle that lie on the base and the height. So the base is this side of the triangle, and this is the height. We can't actually make all four of them lie on the base and the height. So I want to first have you do a quick, just 30-second pause. See if you can draw the rectangle in there. 4, 3, 2, 1. 30-second pause. Just draw the rectangle in there. Alrighty, so hopefully you did that. Let's draw it together. So the rectangle is going to look something like this. Something like this. So we have this side, which is lying on the height of the triangle, and this side, which lies on the base. Okay. So now that we know what the picture looks like, I want to have you do a proper pause for 6 minutes to try this question. 4, 3, 2, 1. Pause it for 6 minutes to try this one on your own first. That's really going to be important. It's important to do that to assess how well you can solve problems like these on your own, because ultimately that's what you're trying to work up to. Alrighty, let's go ahead and talk about it together. So I need to assign some variables. So let me call this length x, and that vertical distance, I'll call this y. All right, so now we want to write our objective equation. So our objective is an equation for the thing that we want to maximize or minimize. In this case, that's the area. And the area of this rectangle is x times y. Okay, now we got to think about constraint. So a constraint. Okay, so we'll need some other equation here based off of that involves x and y. So in my picture, if I look at this small triangle, let me just draw it here. If I look at that small triangle, that triangle is similar to this larger one. It's similar, it's hard to draw it a little bit, I'm running out of room, to that larger one. And the larger one, this is 12, this is 16. And the smaller one, this vertical distance is y. And the horizontal distance is 16 minus x. 16 minus x, because 16 is this whole length. Okay, so if we set up a proportion, that could look like we would get 12 over 16. There are a few ways we can do this, but 12 over 16 would be equal to y over 16 minus x. Okay, so now that we have that, we would want to use our constraint to be able to substitute in for the objective. I'm going to put a dot, 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 and leave those details for you. It's going to be really great practice to work it out. But I don't think that's going to be too bad, so I'm going to leave it as a practice, and I'm going to focus on sort of the next key concept. So it turns out that our area function is 64 over 5x minus 4 over 5x squared. So when we take the derivative of this, the derivative will be 64 over 5, and then minus 8 over 5x squared. So from here, we would find critical numbers. I'm just going to put a dot, 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 and leave those details for you. It's pretty quick, but still, I'm going to leave those for you. It's just some algebra from here. Leave those details for you, and it turns out that our critical number, there's just one here, it ends up being x equals 8. Now I have to test this critical number to see if it corresponds to a max or a min. And in the previous video, we saw that there's 3 ways to do that. If our interval is a closed interval, we could use the closed interval method. Or we could also use the first derivative test plus some justification, or the second derivative test plus some justification. For our problem, it'll turn out that all of those will work, but I'm going to use the second derivative test plus some justification plus justification. I'm doing it in part just to get practice with it, because in the last video I did it with the first derivative test plus justification. The other reason I'm doing it with the second derivative test is I notice, whoops, I miswrote my first derivative. It should have just been 8 over 5x. Okay, I notice that the second derivative is going to be really simple. In fact, if I take that second derivative, the second derivative is just negative 8 over 5. And that's always negative. This is always less than 0. So if I were to draw a graph, and I were to label my critical point at 8, and I draw a point there, this is a critical number, and I know my derivative is 0 there, so it's going to be flat. The fact that my second derivative is negative means my graph is going to be concave down. So that gives me a local max there. That's what the second derivative test says. But in optimization questions, we're looking for absolute maxes and absolute mins. So we need to somehow justify why this local max is an absolute max. So we've seen that justification in the lecture. Let me remind us what it is. We would say, since my second derivative is actually less than 0 for all values of x, because it's always just negative 8 over 5, the local max that we have at x equals 8 is also, what this means is my graph just stays concave down the whole way. And if it stays like that, that has to be an absolute max. So this local max is also an absolute max. All right, and that's what we wanted. Last thing I got to do is make sure to answer what the question wanted. And it wanted the dimensions of the rectangle. So one of those dimensions was x. And we got x was 8. And from that, we could find, with a little bit of arithmetic or algebra, we could get that y is 6. It's just 1 or 2 steps to get that, but I'm going to leave that for you. And I'm going to box this. This is our answer.